Hello everyone, my name is Tanmay Agarwal and on behalf of MIDAS IT, I welcome you to this webinar on two-span continuous PSC Composite I-girder bridge. So the overview of the bridge that we'll be looking today, it's a two-span continuous bridge. Each span is 25 meters and it consists of 5 precast post-tension girders which are spaced at 3 meters center to center, and we'll be seeing the behavior of the bridge under the application of static, pre-stress and moving loads. So this webinar will be covered in two sessions. In the first session, we'll see how to generate the composite sections in MIDAS using sectional property calculator and the definition of boundary conditions, as well as the application of static, pre-stress and moving loads. And in the next session, we'll see the construction stages in MIDAS and the definition of composite section for construction stages in MIDAS, and finally the design as per IRC 112. So this is the type of model that we'll be generating today. So two span continuous, each span is 25 meters, and for the continuous part we have the mid diaphragm which will be integral with the girders for both the spans. The total width is 15 meters and the code for moving loads will be IRC 6, and for time dependent material properties, that is creep and shrinkage and compressive strength for concrete, we'll follow IRC 112. So as you can see, these are the dimensions for the sections that we'll be taking for the mid section and end section. Apart from these, we'll also have the tapered sections. So this is the elevation, and so 2.5 meters we'll have the support section, then 2 meters tapered section and 8 meters mid section. Apart from that, we'll be having two end diaphragms, and we'll now see the construction stages. So in construction stage 1, the pier and the pier cap will be erected. In construction stage 2, only the girders for the first span will be activated, which will be resting on temporary supports. Then in construction stage 3, the girders for second span will be activated, which will again be resting on temporary supports. Then in construction stage 4, the diaphragms will be casted, but the bridge will still be resting on temporary supports. And at this stage, the wet concrete load will start acting, which implies that the casting of slab has begun. Then in construction stage 5, the slab will be casted and the bridge will be shifted from temporary supports to permanent supports. And then construction stage 6 is that will be used for analyzing the long-term effects. So now let me take you to the software for a live demo. So this is the general working window of MIDAS, and here we have the works tree. As soon as we enter the information, any information that will be shown here in the works tree. So first of all, we'll start by adding the material properties. For doing that, we'll go to Properties tab, Material Properties, Add, and first I'll add the material for girders, which I'm considering as M40, and apply. So you can see that the material is added here. Next, M30 grade for the slab. Then we'll add a material for diaphragm. Now, even though it is same as M40, but we'll add it separately because we don't want to consider the time dependent effects, that is the creep, shrinkage, as well as the compressive strength for the diaphragm. That will be considered only for the girder and slab. That is why we need to add a separate material for this. Apart from this, we'll also add the material for our dummy members. Now, when we define the composite sections, the program calculates the equivalent weight of the concrete slab and then considers it with the girder. So that is why we need to add the dummy members, but we'll make the weight density of these dummy members as 0, as the weight has already been considered in the composite section. And finally, I'll add a material for the tendons, the pre-stressing tendons. So as per Indian standards and FE 490. Okay, so all the materials have been added. Now I'll define the time dependent material properties. But before doing that, I'll change the units to Newton millimeter. Now I'll add the creep and shrinkage properties, add, And first of all, for M40 creep and shrinkage, as per IRC 112, compressive strength at the age of 28 days will be 40, 70% humidity, and this notional size is dependent on the cross section. So after we define the cross sections and the geometry, this will be calculated automatically by the program. And so we need to enter a random value here. The actual value will be calculated after we've defined the sections and the geometry. Apply. Next, for M30 creep and shrinkage, 30, and OK. Now I'll define the time dependent material properties for compressive strength. So add for M40 compressive strength as per IRC 112. Now, mean compressive strength of concrete at the age of 28 days, FCK plus delta F. As per IRC 112, it is 40 plus 10. And I'll select normal cement, redraw graph. So this is the variation that we'll be considering for M40 grade. Next, for M30 compressive strength as per IRC 112 and 30 plus 10 normal cement, redraw graph. Okay. So we've defined the time dependent material properties, but we need to link these properties with the corresponding materials. So for doing that, I'll use this option material link. Select M40 creep and shrinkage, M40 compressive strength, link it with M40, the same thing for M30, add, close. So we've defined all the material properties. Now we'll be defining some sections. So as I told you that I'll show you how to generate the sections using sectional property calculator. So for doing that, first of all, I'll change the units back to kilonewton meter and then go to tools, sectional property calculator. So in SPC, I'll be importing a drawing from AutoCAD, generating the section and then exporting it to MIDAS. So it is important to note that the units for all the three programs, AutoCAD, SPC and MIDAS, should be same. So meters. Okay. I'll import the drawing here. Import AutoCAD DXF. Okay. So as you can see, this is the mid section that we have generated and the support section. Now these are the drawings and now we'll generate the sections. But before doing that, I'll define the materials. So materials, I'll add M40 3.1622 0.2 and a density of 23.6. Apply. M30. Okay, so we've added both the materials here. Now we'll generate the section. So go to section and composite section, generate. So we'll add the name mid section consisting of two parts with the base material M40 and apply. So as you can see in the message window, new composite section with two parts is generated. I'll do the same exercise for support section. Again, two parts and base material M40 and apply. Now we'll be adding the parts to these composite sections that we just generated. So add part, part ID 1, name girder, material M40. I'll select the girder for the midsection and apply. Next, part ID 2, slab, the material as M30. Select the slab and apply. Next, I'll be doing the same for the support section as well. So support section, part ID 2, slab, material M30. Select the slab, apply. Sorry, I'll first add the girder. part material as M40 and select the girder and apply, and then to slab M30, select the slab and apply. So now these sections have been generated. So now we'll calculate the composite section properties for these sections, and then we'll export these sections to MIDAS. So for doing that, I'll go to property, calculate composite property. I'll select the mesh size as 0.1, that is 100 millimeters. Select this and apply. So in the message window, it shows that the properties of composite section are calculated. The same thing for the support section and apply. So again, the properties of composite section are calculated. Now we need to export these sections into MIDAS. For doing that, I'll again go to model, section, composite section and export. So I'll add the file mid section, save, and select the mid section, apply. I'll add one more file, support section, save, select the support section and apply. So now these two .sec files have been generated, which we'll import directly in MIDAS Civil. So going back to the software, now we'll go to properties, section properties, add, and in the composite tab, I'll select composite general. Using this option, import SEC files, I'll import the mid section. Okay, so this section is imported and all the properties are displayed here. Mid section, I'll change the offset to center top. So the modeling and all will be done with respect to this point. Okay, and apply. So this section is created. Now we'll create one more support section. Again, import SEC file, support section. Okay, and if I click on show calculation results, so this will show all the cross-sectional properties before and after the composite action has taken place. And okay, so these two sections have been imported in MIDAS using SPC. I'll import the rest of the sections from another MIDAS file to save time, and then I'll define the tapered sections here. So import from another file. These two sections have been generated, and I'll show the generation of the tapered sections. The rest I'll be importing. So these sections have been imported. Now let me define the tapered sections. So for doing that, I'll go to the tapered tab and select composite general section. And now first of all, I'll define support to mid section. For the I end, I'll import the SEC file as support section. And for the jth end, I'll import the mid section. I'll change the offset to center top. Okay. And if I click on this, so we can see the sectional properties at ith end and jth end, both before and after the composite action has taken place. Close. Next, I'll define the section mid to support. For that, the section at ith end will be the mid section, and at jth end will be the support section. And okay. So all the sections have been defined. I'll just show you the rest of the sections. For the pier, we have defined a solid track type section with these dimensions. For the pier cap, we have three parts: the pier cap mid, which is a solid rectangle type section, and pier cap left and right, which are again tapered sections. So for doing that, we went to tapered tab and selected solid rectangle type, and we've entered the dimensions at both ith end and jth end. So like that, we have defined the pier cap left as well as pier cap right. Apart from this, we have defined the diaphragm members, the end diaphragm, Now in this case, we can see that the point of reference for modeling is a bit shifted up to the top. That is because we have provided the offset as center top and then a vertical offset of 0.25 meters. This is because the diaphragm will be added below the slab, and the thickness of the slab in all the sections that we have considered is 0.25 meters. So that is why this offset. And the same for mid diaphragm also. Apart from this, the dummy members that we have defined. Now, while defining these dummy members, we need to ensure that IZZ is kept as 0, because we don't want the participation of these dummy members in the longitudinal stiffness. That is why. So the definition of the sections is complete. The materials is complete. Now we'll start working on the geometry. So basically I'll be generating the right span first, and then I'll use the mirror option to create an exact replica on the left hand side. So I'll go to node slash element, create nodes and apply. So a node is created here at origin, and now I'll use the extrude option to generate girder from this node. So I'll select node to line element, M40 midsection, unequal distance in the x direction, 0.5, 24 at the rate 1, 0.5, and using this option select all, the node will be selected and apply. So as we can see, the section, the girder is generated. Currently we need to have 2.5 meters support section, then tapered and then mid, so we'll allot them accordingly. So I'll go to the works tree, switch off the 3D view and select 2.5 meters 2.5 meters and allot support section. Next I'll be selecting 2 meters and support to mid, drag and drop this section, mid to support, drag and drop. So now first girder is complete. As you can see, there are some irregularities here, so that will be taken care of when we'll define the tapered group. So now I'll generate the dummy members. So for doing that, I'll select these nodes and translate them in the y direction minus 1.5 meters, and using these nodes I'll extrude the dummy members. So using this option, select recent entities, all the nodes are selected, and then extrude dummy members and y direction 1.5, 4 at the rate 3, 1.5, apply. So the dummy members are generated now. Now we need to copy the girder at these locations, but before doing that, I'll generate the nodes on the girder for our supports, for our temporary supports, and also the nodes at the end girders for diaphragm. So for doing that, I'll select these elements and divide, use the option divide in two equal parts and apply. So these nodes have been created, and so as I told you that this span I'll be using the mirror option to replicate it to the left hand side. So that is why this central member here will be our mid diaphragm. So I'll delete these two elements, select the rest of the elements, and first of all assign the material diaphragm, and again use this option, select previous, assign the section mid diaphragm. Now after this, I'll copy the girder at other locations. So select the girder and translate. So copy equal distance, click on the first node and the second node, it automatically calculates the distance 4 times, and I'll check on this option, intersect node element, node attributes, element attributes, and apply. So this has been created. Now I'll add the diaphragm section here. So for doing that, I'll use the create elements, select the material as diaphragm, member as end diaphragm, and the nodal connectivity from here to here. Now this much has been done. Next, I'll be defining the section for pier cap and pier. So for doing that, first of all, I'll divide these two elements into equal parts so as to generate the bearings below these diaphragms that will act as our permanent supports. So these two nodes have been generated, and now I'll translate these two nodes in the z direction minus 2.25 minus 0.1, and the same thing will be done for the nodes for the permanent supports on these diaphragms also. So I'll first divide them also in two parts and select these two nodes also, and apart from this, all the temporary supports will also be at the same locations, but the temporary supports will be beneath our girders. So I'll select all these nodes as well, and these two nodes I'll translate them in the z direction with this distance and apply. As you can see, the nodes for our temporary supports as well as the permanent supports have been created. Next, I'll be drawing the pier cap section here. So for doing that, create elements M40 and pier cap mid, nodal connectivity from here to here. Then I'll select this recent entity and divide it in 4 equal parts and apply. And I'll also copy this node to the y direction 1 meter, apply, and the same for this node to y direction minus 1 meter and apply. And I'll create elements here for the pier cap left and the right section. So pier cap left section, nodal connectivity from here to here, and the pier cap right section with the nodal connectivity from here to here. So if we see in the 3D view, this is currently pier cap mid section. So we need to allot, I'll select this section and pier cap left, and then I'll select this section and pier cap right. Now when I see the 3D view, so again the irregularities are coming here. That will be resolved when I define the tapered group. Before that, I'll define the section for pier. So I'll translate this node in the z direction minus 1.5 meters, and then using this node, select the recent entity, extrude option, M40 pier, and in the z direction minus 7 meters and apply. So the geometry for the first span is complete. But one more thing, we'll have to add the dummy members at this location and this location. These dummy members will be used when we add the superimposed dead load for the crash barrier. So dummy members and dummy section here to here. All right. So now in the 3D view, this is complete. And so now before making an exact replica of this to the left hand side, I'll add the boundary conditions as well, and that will again be replicated on the left hand side. So for doing that, first of all, I'll have to add groups. So I'll go to groups, boundary group, new, and I'll name it as substructure boundary group new. I'll name it as temporary 1 add. This will be used for the first span, and then temporary 2 and add for the second span, temporary supports, then permanent supports add, and then substructure supports add and close. So basically when we define the construction stages, as I was telling you, the activation and deactivation of supports, so we'll have to activate and deactivate the groups. So as soon as I enter any boundary condition, I'll be defining the group as well, as we'll be dealing with groups in construction stages. So first of all, I'll add the boundary conditions for substructure. So go to boundary, add rigid links to simulate the rigid behavior, and select the boundary group as substructure rigid body. So all the degrees of freedom will be restrained, and I'll select the master node as this node and the slave node as this. This is to simulate the behavior between pier and pier cap, and click on apply. So the link is created in the substructure boundary group. Now I'll also define a fixed support at the bottom of the pier in the same group. So for doing that, define supports, restrain all degrees of freedom, select the boundary group as substructure, and select the node, this, and apply. So the boundary conditions for the substructure have been completed. Now I'll add the permanent supports. So for adding the permanent supports, as we know that the permanent supports will be just below our diaphragm, the mid diaphragm and the end diaphragm. So for doing that, first of all, I'll be adding rigid links from this node to this node, and then the elastic links which will be used to simulate the bearing conditions. So rigid links, and I'll measure the distance between the two supports, that is 9 meters. So boundary group name as permanent and rigid body. Master node will be this, and the slave node will be this. I'll use this option copy rigid link in the y direction minus 9 meters and apply. So these two have been created, and the same will be done this side also. So in this case, the master node number will be this, and the slave node will be this, and apply. So two rigid links have been created here as well. Next, I'll add the elastic links for the simulation of bearings. Now for that, I'll go to elastic links, select the boundary group as permanent and general elastic link. So for this, basically, we'll simulate the simply supported condition. So for doing that, I'll for this node here, all the degrees of freedom will be restrained. So I'll add the value 1E8, basically very high values of stiffness, as we won't be allowing any movement here. 1E8, and the two nodes will be selected, this and this. Now, as you can see in this elastic link, that the X direction is the vertical direction, Z is the longitudinal direction, and Y is the transverse direction. So whenever we are adding the stiffness here, we need to keep in mind the orientation of this axis. Now when I'll add the elastic links for the bearing here, I'll just free the movement in the Y direction and select the two nodes, this and this. Same thing for the nodes here as well. So for this side, I'll allow the movement in the longitudinal direction. So make this as 1E8, this as 1000, and select the two nodes as this and this. And next, for for these two nodes. So here I'll be allowing the movement in the longitudinal as well as the transverse direction. So I'll select the two nodes as this and this and close. So the boundary conditions for the permanent supports have been added, and now I'll define the conditions for the temporary supports as well in this span. So basically I'll consider this as span 2, which will be activated at a later construction stage. So the temporary supports will be added in temporary 2 group. So I'll go to rigid link and rigid body, the group name as temporary 2, zoom in here and select the master node as this, and start it from here. So select the master node as this and the slave node as this, and copy rigid link in the y direction 4 @ 3 meters and apply, and the same for the end span. Select the master node as this and the slave node as this, again copy in the y direction and apply. And now I'll add the bearings here. Now for simulating the simply supported condition, there are two options. Either we can use the stiffness entered in the elastic link data, or we can provide rigid type elastic links and then add the boundary conditions at the bottom of the nodes. So here I'll be doing that. I'll select the rigid type elastic link, and in the boundary group temporary 2, I'll use this option copy elastic link 4 @ 3 meters. Select the two nodes, this and this, and the same for here also, this and this. And now I'll add the supports at the bottom nodes to simulate the simply supported condition here. So for doing that, I'll just undisplay the elastic links and select the bottom nodes, and I'll add the support condition. Go to define supports. I'll select D all and RX and RZ in the group temporary 2 and apply. And here I'll again select the bottom nodes, selecting the bottom nodes, and here only DZ will be restrained. So apply. So now the boundary conditions and the geometry is complete for the right span. Now I'll use the mirror option to create the exact replica on the left hand side. So for doing that, I'll go to node and element and use this option mirror. Go to the top view, mirror about the YZ plane and X as 0. I'll select all the elements and intersect node element, as well as copy the node elements and element attributes and reverse the element local axis and click on apply. So as you can see, there are a lot of warnings coming here that some elements are overlapped at the same location. So for avoiding that, I'll go to properties and I'll go to structures and click on this option, check duplicate elements. So as soon as I click on this, the duplicate elements are deleted. So there is no repetition of any element. So this is the complete geometry, but here as we can see that some nodes are still left. So for creating those nodes on the left hand side, I'll select these nodes and use the option mirror nodes, keeping everything same, and I'll check on this option copy node attributes and click on apply. So now the complete geometry is done and we can see the boundary conditions by just going to display options, boundary, and selecting all and OK. So the supports have been added here, as well as the elastic links have been added, but we need to add the rigid links here. So for doing that, I'll zoom in here and unsee all the supports. Okay, and I'll add the rigid links here. Boundary rigid links, and the boundary group name, first of all, I'll add for the temporary supports. So temporary 1, and select rigid body and the master node as this. The master node as, I'll do it from here, the master node as this, and the slave node as this. Click on copy rigid link in the y direction 4 @ 3 meters and apply. And now for the midsection, so I'll again be selecting the master node as going to the top view. The master node will be this one, so I'll select the master node, uh, this one, and then the slave node, that will be this one, and apply. So this has been generated for the first span. And now for the permanent rigid links, so the master node will be this, and the slave node will be this. I'll select the distance as 9 meters and apply. And the same exercise for the mid span also. So for that, the master node will be this, and the slave node will be this, and apply. So these two have been created here. So close. So now all the support conditions and everything is added in this model. So, but here, as we can see that still there are some irregularities in the section. So for doing that, I'll be assigning the tapered groups. Before doing that, I'll just unselect all the all the rigid links. So on display and undisplay. All right, before doing that, as we can see in the work tree, that this section here, support to mid. Now this section, as we have created, as we have used the mirror option, so these sections have been mirrored here, but these sections should be here. So when I select the mid to support, these sections here should be support to mid. So I'll use this option, unselect by window, unselect these elements, only these elements are selected, and drag and drop the support to mid, and then mid to support. Okay, and then support to mid. So these sections here should be mid to support. So I'll unselect these two and mid to support, drag and drop. So now support to mid sections and mid to support sections. Both have been created here. Now I'll define the tapered groups. For doing that, I'll go to properties and tapered group. I'll define this one as mid to support and add. Next, for support to mid, select the members from here and add. The same exercise for pier cap left. The elements list will be this one, and add one more for pier cap right, and the element list will be this one, and add. So now if we see the 3D view, the geometry is fine. Here we can see the tapered sections have been added perfectly as well as in the pier cap section. So now the complete geometry is done and we'll start with the application of loads. So before adding the loads, I'll have to create the groups for loads, because again when we're defining the loads in the construction stages, we'll be dealing with the groups only. So I'll go to group and I'll define the load group first of all for the self weight and add, then for SIDL crash barrier add, for SIDL bearing course add, and one for wet concrete load add, and then one for pre-stressing loads, pre-stressing 1 from 1 to 4 add, and then pre-stressing 2 from 1 to 4 add, and close. Now I'll be defining the loads here. So for doing that, I'll have to add the load cases first. So going to loads tab and selecting the static load cases option, I'll first of all add self weight, and I'll define all the loads as construction stage loads, as we'll be defining all the loads in the construction stages. So construction stage load add, SIDL bearing course add, crash barrier add, and then pre-stressing add, wet concrete add. Okay, so here in the worksheet we can see that all the load cases have been added. Now for the self weight, I'll use the command self weight and select the load group as self weight and the load case also as self weight in the Z direction as -1 and add. So the self weight has been added. Next, I'll be defining the loads for bearing course and crash barrier. So those will be basically uniformly distributed loads. So I can use this option element loads and select SIDL crash barrier, and I'll the direction will be global Z. And in the 2D view, as I told you that these elements will be carrying the self-weight crash barrier load. So the load for self-weight crash barrier that we are considering is -9 kilonewtons, and I'll select the girders. I'll select the dummy members on which the load will act and apply. So the load is added here. Next we'll add the load for bearing course. So SIDL bearing course, SIDL bearing course, and the load will be -6.5 kilonewtons, and these loads will act on the girders. So when I just want to activate the girders here, so for doing that I'll go to the works tree again, select the mid section and activate it. Right click on the support section and click on active plus, then right click on support to mid, active plus, and mid to support, active plus. So these are the girders on which the load will be acting. So now I'll be selecting this option, select all, and apply. So these loads have been added here. So in this way we have defined the SIDL bearing course and the SIDL crash barrier. I'll also define the load for wet concrete that will again be acting on my girders. So load case wet concrete and load group again wet concrete, and the load is -18.8 kilonewtons, and I'll use this option to select previous and apply. So all these loads have been added as we can see in the works tree, and I'll use this option to activate all. Now I'll be defining the moving loads. But before defining the moving loads, we need to renumber the elements. So that is because when we'll be defining the moving loads, we'll be defining the lanes. So the lanes will be defined from this span to this span, but we have defined these elements after these. So it is important to renumber all the elements such that the number for these elements come before these elements. So that is why I'll go to node and element and use this option renumber element ID, select node and element all, and I'll select the preference as this and apply. So the renumbering is done, and now I'll define the moving loads. So for the moving loads, in this case, I'll be considering 3 lanes, and as per IRC 6, so for 3 lanes, we'll have 2 load cases. The first load case will be 3 lanes for class A, and the second load case will be 1 lane for class A and 1 lane for 70R. So for doing that, I'll go to this tab loads, moving load, select the moving load code as India, and first I'll define the traffic lanes. So go to this option and add. Before doing that, we'll have to make a group of all the dummy members which will be used to define the lanes. To define the lanes for our grillage model, we'll have to create a groups of all the cross beams, which are in our case the dummy members. So I'll go to group and I'll create a new structure group which will be defined as cross beams and add, and in this group I'll add all the dummy members as well as the, so I'll activate the dummy members and I'll activate the diaphragm members, because both of these will be acting as cross beams for the definition of traffic lanes. So all these have been added here, activated here, and now I'll select all and drag and drop cross beams group, and now I'll activate all. So this group has been created. Now I'll define the traffic lane. So add, and first of all I'll name it as 3 class A lane 1. First of all I'll define the lane with an eccentricity of minus 0.9 meters with an impact factor of 0.2. So here the impact factor that we are adding 0.2, so the program will take it as 1.2. And vehicular load distribution as per cross beams, the group is cross beams, moving direction is both, and I'll select 2 points by picking here and here. So this data has been entered and okay. So this lane has been added here. Yeah, so in this case it's showing an error that it does not intersect a cross beam. So that is because the eccentricity that we have added is, there is some problem with the eccentricity. So for that, what we'll be doing is the eccentricity actually in this case should be positive. So I'll delete these and again add as 0.9 meters and the impact factor of 0.2 meters cross beams, and I'll select this element and this element and click on OK. So now the lane is added and we can see the lane using this. So this is the first lane that we have created, and similarly we'll define the other lanes. So add 3 class A lane 2, eccentricity as 0.9 meters and the impact factor as 0.2 cross beams and 2 points. I'll select this girder and this point and OK. The second lane is created. Now the third lane, 3 class A lane 3, eccentricity as 0.9, impact factor 0.2 and cross beams group, and 1 point this and 1 point this and OK. So the 3 lanes for our load case 3 class A have been created. Next I'll be creating the lanes for 1 class A plus 170R load case. So for that add, so class A plus 70R lane 1, eccentricity as 0.9 meters, impact factor as 0.2, cross beam, group cross beam, 2 points, this and okay, and one more for class A plus 70R lane 2, and in this case the eccentricity will be minus 2.1 with an impact factor of 0.2 meters, oh sorry 0.2, and vehicular load distribution cross beams, and 2 points. I'll select this point and this point and okay. So now all the lanes have been added. Next we'll be defining the vehicles. So for doing that I'll use this option vehicles, add standard and use IRC 6 class A vehicle and apply. Next I'll be defining the 70R vehicle and okay. So both the vehicles have also been added. Now we'll define the moving load cases. So for doing that I'll use this option moving load case, add, and first of all I'll add 3 class A. Uncheck this option auto live load and click on add. Now I'll select the scale factor as 1. Minimum number of loaded lanes will be 0 and maximum will be 3. The vehicle will be class A and I'll select these 3 lanes which we generated for this load case and keep them in the selected lanes and okay and okay. We'll add one more load case that will be for class A plus 70R. Uncheck this option, click on add, and the maximum number of loaded lanes will be 2. So in this case we'll first select class A, and in the lane 1 we'll keep the class A vehicle and click on OK. Click on OK and we'll add one more 70R in the second lane and OK. So these two have been added here for this load case class A plus 70R. So we click on OK and this definition is complete. So far we have completed the geometry of the bridge. We have defined all the materials and the section properties, and we've defined the load cases for self-weight, superimposed dead load, wearing course, crash barrier, and the wet concrete load, as well as the moving loads. So in the next session we'll look at the application of pre-stressing loads and the construction stages, as well as the composite section for construction stage and the analysis and design. Thank you all for attending this session, and for any further queries please feel free to contact us at techsupport@midasit.com. Thank you.